Hello students. So in the previous lectures on magnetostatics, we discussed about the magnetic field due to currents. We discussed about line currents, surface currents and volume currents. And we, using Biot-Savart's law or Ampere's law, we could calculate the field, magnetic field due to those currents. We also learned that the magnetic phenomena is essentially because of charges in motion. So, as you encounter every day various types of magnets, you must be wondering, so if all magnetic phenomena are because of charges in motion or currents, so where are the currents or where are the charges which are in motion inside these materials which are showing magnetic effects? So to understand that, you need to first understand that you need to first kind of think is that these macroscopic objects which you encounter, they consist of many atoms and molecules. And in each of these atoms, there are electric charges in motion, and that's your electron, right? So, and these electrons, they not only orbit around the nuclei, they also have something known as spin associated with them. So these spinning electrons or orbiting electrons constitute tiny current loops. Okay, that's very important. So because these are charges, they are either having a spin or orbiting around the nucleus. So you can think of them as some kind of a current loop. Now once you have current loops, you can associate a magnetic dipole to them. So in other words, the electrons in these atoms will have an associated dipole. So in particular, if you think of the spinning of this, the spin associated with these electrons, we can associate one dipole corresponding to the spin of the electron. Now, in general, there are random orientations. I mean, these dipoles will orient in all possible directions, and then they will cancel each other. Okay. However, when you apply one external magnetic field, so there can be a net alignment of these dipoles. Okay, and then we call these materials are magnetized. Okay, as magnetized. Now, depending upon the state of magnetization, we can have various kinds of materials. So, one kind is paramagnetic. Now, here the magnetization is parallel to the applied field. Okay. Now, what do I mean by parallel? So, as I told you, these dipoles which are associated with the electrons motion. So, these dipoles tend to orient parallel to the applied field. So, those materials are known as paramagnetic. And then there is diamagnetic materials where the magnetization is opposite to the applied field. Okay. And then there are another class of material known as ferromagnetic, where although the magnetization is parallel to the applied field, whenever there is a field present, even if you switch off the field, these materials retain the magnetization. Okay, that's very important. So even there are no field, you apply and you switch it off, there are some remnant magnetization in these materials. Okay. So now in this kind of lecture, we'll come across a quantity which I should define now is M, and that we call as magnetic dipole moments per unit volume. We'll use that in so this is a measure of magnetization, and we will use this quantity in subsequent part of this lectures. So now let's okay, before I discuss about these materials or these effects, paramagnetic, diamagnetic, and ferromagnetic, I should tell you that if you in-depth analysis or in-depth understanding of these effects will require knowledge from quantum mechanics, some quantum mechanical ideas, so which is not the scope of this lecture. So we will kind of give a discuss a very simplistic classical way or classical view of these paramagnetic and this kind of materials. Okay, so now let's discuss paramagnetism. Now, before I really discuss that, let's first, if you want to understand paramagnetism, we should understand what happens to a dipole in a magnetic field. I mean, first of all, whether it experiences a force or a torque. So we should first know that, because then only we'll talk about the alignment of the dipoles. So as I told you, these materials will have tiny current loops associated with these electronic motions. So we can consider at least one such tiny current loop, and then so there will be dipole assigned to that current loop, and then ask questions like what happens to this individual current loop or the dipole when you apply an external magnetic field. So here I have put one such current loop. For simplicity, I have considered a rectangular current loop, but the results do not change for any other shape as well. And so now let's say that there is a magnetic field along the z direction, and these current loops is making an angle theta with respect to the z axis. So which means it is so the origin of this loop is at the center of the loop is at the origin, and then the current is flowing like in anticlockwise direction, and the loop is tilted at an angle theta with respect to the axis. And naturally, the magnetic moment, the dipole moment m, will have an angle theta with respect to the axis. Okay, because the m is perpendicular to the loop, right? Okay, so now with this kind of arrangement, let's ask first some questions about the force and the torque. So the question is, what is the net force on this current loop? And I have already written the answer is 0. You think about it. I mean, we'll answer this in more detail in the latter part of this lecture. However, so the net force on this current loop is 0. You can also analyze, each side. For example, if you take this side, so this current loop has side A and B. It's a rectangular current loop. So one side is A, one side is B. Now, if you look at this now and calculate what is the force on this side, so you can analyze the force on each side. So this side, it's if you look at the force or the dl cross b, as you know, so it turns out that the force is along this direction. Okay, so for this side, you will have the force which will be like this direction, and for this side the force will be along this direction. So they are equal, but they will cancel each other. They're equal and opposite. Similarly, if you want to consider these two sides, the B side, so again the forces will be equal and opposite. However, because of the tilt, this force will exert a torque. This will have a torque. So the loop will experience a non-zero torque. Okay, that's important. It will experience a torque. And how do you calculate the torque? Well, a torque is nothing but R cross F. So there is a vector here. Yeah. So the torque is nothing but R cross F. And you sum over the terms. So so now you have two sides. So what you do, if you do the R cross F, you will see that it is A by 2. So because this is your R for one particular side, so it will be A by 2. Of course, R cross F, and then there is a cross product, so there will be sine theta and x cap. Okay, so the direction which should be perpendicular to both R and F. Okay, so the F direction is this way, and the R direction, which is along this way. Okay, so the R cross F will come out of the page. Okay, I'll just erase this. So now that you know, then you can just do the algebra and you will see that the torque comes out to be A F sine theta x cap. And of course, the magnitude of the force is nothing but I dl cross B magnitude and dl cross B for that side. So you are calculating the magnitude of force for this side. So dl and B is uniform. Okay. So when I say B is uniform, you can take out B from this integral, and then what will end up is the dl integration, and dl integration will give you B, and so that is IBB. Okay, that's your force. Now you plug this value here. So the torque becomes AB I multiplied by V and sine theta x cap. Now ABI, this part, so AB is the area, I is the current, and so then AB and I should give you the dipole moment. Okay, and then you have B here, and so your dipole moment M B sine theta x cap, and that is nothing but your M cross B. So now you can write the torque, the final term, the torque on a magnetic dipole in a uniform field is M cross B. Okay. Now, what is the effect of this torque? So this torque tends to align the dipole parallel to B. Okay, that's very understandable because of this cross product terms. So this will try to align the dipole parallel to B. Now, if it does that, now imagine, as I already told you, each atom you can associate a dipole moment with each electron due to its spin. So you have a dipole moment associated with spin. So any external magnetic field will align or tend to align these dipoles along the field. This is essentially the mechanism which is responsible for the paramagnetism. So we have so in summary, what you can think of is that there is an electronic spin, and because of the spin, you can assign a dipole moment. And when you apply an external field, these dipole moments will tend to align parallel to the field, and that's why you will have a net alignment along the field, and that is the paramagnetic effect. Okay. Now there is so of course, I mean, every macroscopic objects will have atoms inside them. So you may think that paramagnetism is universal. However, what happens because of quantum mechanics? Sorry, because of Pauli's exclusion principle, which is in quantum mechanics, these actually electrons come in pairs. I mean, they tend to pair up the electrons with opposite spin. Okay, so and which in effect cancel the dipoles. Therefore, paramagnetism is not universal phenomena. It is most often observed in atoms or molecules with odd number of electrons. So when I say odd number of electrons, which means you will have some electrons which are unpaired, and those electrons will be responsible for the paramagnetism. Okay. But even then, even if you have unpaired electrons, actually this and which may experience a torque, the alignment is not really a perfect alignment because of thermal collisions, which will destroy these alignments. Therefore, I mean, you don't get a perfect alignment with such paramagnetism. So now. So now what here we have assumed a uniform magnetic field and we calculate the torque. And as I asked you questions there, what is the force on the current loop? So let's now look at that into more details. So our next discussion is to calculate the force on a dipole. I have already told you the answer that in a uniform field, the force is 0, and that's precisely the reason. Because B is uniform, you can take B out of this integral, and then you will have the result as 0. Okay, because the dl integration along the closed loop will give 0. So the force, the net force on a dipole in uniform field is 0. But when the field is non-uniform, then things are different. So in case of non-uniform field, now you have to do this integration explicitly for each side, right? Because now B you cannot take out of the integration. So you have to perform the integration for each side. So for again, for simplicity, let's consider a square loop. So let's solve this problem. There's an example for you to see what happens for a non-uniform field. So now we have again a square loop. Let's say it is side is each side having epsilon. So here is the origin. Now as B is non-uniform, first you have to think what happens to B along this line, along this line, along this line, and along this line. So if you look at this line, so here you are only varying Y here. So effectively, your B will be a function of B 0, Y, and 0, because nothing is varying here, only Y. Along this line, your Y value is epsilon. So your B will be function of B 0. Your Y value will take the epsilon, and then Z. There will be variation along Z. So accordingly, you can figure out what should be the function, what should be the form of B along all these four sides. So if you plug back those details, you have an integration. So your first side integration will give you Y cap, that's along Y. And as I told you, B will be a function of Y along Y only, because you are not varying any Z and X in X direction. So your B will be B0, Y0, and then dy. Because your DL, you are doing the integration of DL cross B. And DL, so your DL is nothing but dy Y cap for this side. And similarly for this side, your DL will be dz Z cap. And again, B will be 0, B0, epsilon, and Z. So then you do the DL cross B. So and you can write similarly for all the sides. And then since there are, you can, rearrange things, because there are this dy here and Y cap dy here. So you can, rearrange things. And what you have here is that dy Y cap, and then in parentheses you have B0 Y epsilon minus B0 Y0. Now here we can use a smart trick, something known as Taylor expansion. So what it tells you, if this epsilon is small, you can express B0 epsilon Z in terms of the value of B at 0, 0, and Z plus. So then the first order Taylor expansion, that will give you epsilon del B by del Y. Okay, this can be expressed in terms of a series expansions, and the so this is your first term, and the second term is the first derivative of that along the Y. Now, what it essentially means is that your value of B. Okay, so let me go back to this loop, and I will show you what I mean there. So your value of B along this line, okay, that's your B 0, epsilon, and Z. That can be conveniently expressed as value of B along this here 0, 0, and Z here plus epsilon del B by del Y. And here this particular since epsilon is very small, you can safely assume the derivative del B by del Y doesn't vary along this line. Now that makes our life simpler. Now you can plug back. So now what happens is that V0 epsilon Z minus, you can take this term here, V00 Z. So essentially this quantity is nothing but epsilon delta B by delta Y at 00 Z. So you replace this whole quantity with only this one. And you can do the integration now, because this derivative doesn't vary, remains constant there. So you can take out the derivative outside, and then you do the integration of dz, z cap, and then epsilon, and so that will give you another epsilon there. So you'll have effectively epsilon square and I. Okay, and del b by del y, and del b by del y. So that's what I have written here now. Okay. Okay, so you now have the after doing integration, you'll have I epsilon square z cross del v by del y minus. So I have just, you can verify this. So please verify this. Okay, so you will get this from the result from this substitution, and then you do the cross product. Okay, so then you do the cross product z cap cross del b by del y. You expand, you express in terms of the component form del by, and so you'll get all these results there after all the rearrangements. Then you use the fact that del dot b equal to 0, and that effectively means that del by del y plus del bz by del z plus del bx by del x equal to 0. And if you use this and do some rearrangements, you will eventually find out that your force is nothing but m x cap. I think I'm missing a parenthesis here, I guess. Yes, I think I'm missing a parenthesis here. So m x cap del bx by del x plus y cap del bx by del y plus z cap del bx by del z. Now you see m dot b is nothing but mbx, because your m is nothing but mx cap. Okay. So if you look at here, your m is nothing but mx cap, because the loop is actually in yz plane. So your m magnetic dipole moment is nothing but mx cap. So naturally m dot b will be mbx. Now if you want to write the del m dot b, that will give you m delta bx. So with all these thing, you can now write your, because this part is nothing but your delta bx, right? This is x cap del bx by del y, del x, y cap del bx by del y, z cap. So this is your del bx and your m here. So effectively, this right hand side essentially means del m dot b. So now we have a nice looking formula for the force experienced by the dipole in a non-uniform field, and that is nothing but del m dot b. Okay, now before I really end the discussion on these dipoles and the paramagnetism, I would urge you to remember a few things, because there is a natural tendency to compare this dipole with the electric dipole. However, you should remember that unlike electric, so in electric dipole, what you have in electric dipole, you have something like, plus charges and minus charge separated by some distance, right? So you effectively you have, for an electric case, you have a minus and a plus, and then you have a dipole. You can constitute a dipole, right? You also should remember that these plus and minus charges are individual poles. However, in magnetic case, you don't have such distinctions of monopoles. I mean, you may call, you are calling it as a north and south pole, but effectively, what magnetic dipole is nothing but a tiny current loop. So your magnetic dipole is nothing but you have a current loop, and that gives rise to a dipole moment. So please keep this fact in your mind that magnetic dipoles are essentially nothing but tiny current loops. Okay, that's very important to recognize the distinction between an electric dipole and magnetic dipole. So you don't have individual monopoles, individual magnetic monopoles. Okay. So anyway, so this is where I would end this lecture. So here, what we learned here is essentially the mechanism by which paramagnetic effect arises, and about the force and torque on the magnetic dipoles. In the next lecture, we'll discuss about diamagnetism.